Welcome back. So we talked about the measures of central tendency being the mode, median, and mean, and in what levels of measurement would be best to use these. What we're going to do now is look at these mode, median, and mean in a bit more detail. So what is the mode? The mode is the most common score. So when you look at a frequency distribution where you see the most common response, that is what the mode is for that data. It's suitable for all levels of data, but it might not be meaningful for a ratio or continuous data. And it's not affected by outliers, which is a real strength of using the mode. It ensures, because it's just what the most common response is, it's not influenced by the presence of other values. It's just what is the most common response. You can check frequencies in the bar graph to see whether it's useful to understand your data or to report. So here is a nice pretty diagram of some data I've generated, and what I want you to do is have a go at understanding what do you think the mode is. So pause the video and ask yourself the question, what is the mode? And hopefully you've unpaused and you have looked at this diagram and you've thought to yourself the answer is 23. If so, that would be correct, because that is where we see the most common score in this distribution. Now note, despite the fact that it's placed in the middle here, it didn't have to be. So if number 27, so if the age category for 27 had 12 responses, then that would be the mode of the data set. Or if number 16 had 20 responses, that would be the mode of the data set. So it's irrespective of where it's located in the distribution, it's just the most common response in that distribution of data. So we have frequencies and percentages. This is the number of responses in each category, and the percentage of responses in each category. So number is the frequency, the percentage is the proportion of responses you have. And you can use a frequency table to get a sense of how frequently do you see one of those numbers there. So here it's displayed graphically, but you could use a table to say, well, the number 17 appears 6 times in the data set. Here you can also visualize it using a bar or a pie chart. So that's ways in which you can visualize frequencies and percentages. Now, for median, this is the midpoint of the distribution, often referred to as the quartile 2, which has the 50th, which is the 50th percentile. It has 50% of the data. It's not badly affected by outliers. And it might not represent the central tendency if the data is skewed. And we'll look at examples where how the mode, median, and mean shift in the relation to skewed data. If the median is useful, other percentiles might be worth reporting as well. So the median, the main takeaway is it's just the midpoint of your distribution. So if you arrange everything in order, it's what is the middle of this distribution. And the mean is the average score. So you take all of your data that you have and you sum all the scores and you divide them by the number of scores that you have. So you have 5 scores, you add them all up and divide by 5, and that's the average. And it's useful for normally distributed ratio or interval data, but it is sensitive to extreme scores or outliers, which is a problem because if you're reporting the mean and you haven't looked at the distribution of your data, it may not accurately reflect your data. And in fact, you know, a lot of researchers who report their table 1 demographics or any sort of table of demographics in their paper, they often report mean and standard deviation, but there are some measures which you can tell should be quite heavily skewed, but they still report the mean and standard deviation. And in that way, the researchers are not looking at what is the shape of the data and what's the most best way to sort of present that data so that the reader gets a sense of what that data is, because the mean is sensitive to extreme scores and outliers. So sometimes it's inappropriate as well. If you have a bimodal distribution where you have 2 peaks in your distribution and you report the mean, it'll actually take the mean as the 0 value. So the average describes a place where there's actually no scores. And so in some cases, it may not make sense. So every time you're looking at your data, it should be thinking about what is the best representation of what that data is. So here is an example from Andy Field textbook called Discovering Statistics Using R, and you can click this link to get access to the data set as well. And this is where you have a data set about the hygiene, I think, of people attending a festival and day one of the festival, and I think he has day 2, day 3. And what you see here through, if you were just to not plot the data, and you look at the median and mean, nothing sort of seems out of the ordinary. However, if you plot the data, that's when you realize, wow, this is a really skewed distribution. And in fact, there's actually, that skewness is driven by this outlier where the value is 20. Now, I think the scale is 0 to 5. So it doesn't really make sense to have a value of 20 that's there. And so that would be something to remove. So when you remove it, you get this normal distribution, and it really can impact the data in meaningful ways like this. And so what I want to take away from here is when you look at the values, the median is unchanged with the presence of that outlier, but the mean value does change, right? It goes from 1.79 to 1.77. So it's a slight change in the scope of things with the magnitude of effect of the scale being 0, 1, 2, 3, 4, 5. It's not massive, but if you can imagine what that would be if there were multiple outliers that were swinging the results, or if there was a larger data set and the results were in some ways influenced by these outliers, that could have a more meaningful impact on the mean and what we see there. So the main takeaway is that it is sensitive to extreme scores or outliers. So we have to ensure that we're always plotting our data and looking at it and making sure that it actually represents what we think it does. So the distribution of data is key, and that's where it comes down to this plotting, but also we have measures of distribution that we could use. So you measures the shape, the spread and dispersion of your data, as well as the deviation from the central tendency. So how do you decide which statistics to use? Well, again, it comes back to whether your data is parametric or non-parametric. So parametric data, you use standard deviation, skewness, and kurtosis. And for non-parametric data, you can use minimum, maximum values, range, and percentiles. And all of this gives you a sense of the distribution of your data. So what I mean by distribution is here you can see what the spread of the data is. It goes from 0 up until 4. Yeah. And so here's a nice plot that shows you, or a table that shows you when to use the minimum, maximum, range, percentile, variance, standard deviation. Again, I think if you really understand what nominal, ordinal, interval, and ratio are, this will all come into place. So for example, for interval and ratio, they're continuous measures, so you can have a sense of minimum, maximum, the percentiles, and the variance and standard deviation of the spread of that data. So for interval and ratio, it's yes for all of these. For nominal, it's categories with no inherent order, so it doesn't make sense to have min and max on categories or percentiles or variances. So that's why it's all no. And for ordinal, you can have min and max to have the first and last rank to get a sense. Percentile if it's meaningful, and not really standard deviation or variance, because the difference between the categories, it could vary quite a lot. So the standard deviation is the square root of the variance, and I'm not really expecting that to land for you to be like, okay, now I get standard deviation, square root of variance. I'll explain that in a lot more detail in future lectures. But what I do want you to grasp is just that there's a relationship at this stage between standard deviation and variance. So there's a relationship where standard deviation is the square root of the variance. It's calculated with this formula, which we'll go into a lot of detail in future when we talk about variance. And we use the standard deviation for normally distributed data or interval data. Now the standard deviation is affected by outliers, and a cool thing about the standard deviation is you can derive the standard error from the standard deviation and vice versa. So here the standard deviation is equal to the standard error over the square root of n, and you can move this formula around to say, well, standard deviation times the square root of n gives you the standard error. So it's a nice relationship between one and the other. So what are your options really for nominal data? Well, you can, if you recall, nominal data, they're labeled categories. So you can describe this data, but it's a little different. So if you have categories, for example, males and females, you could say, well, which is more frequent? And you could say, well, females in this fictitious data that I'm making up. Females are more frequent than males in this sample, similar to the mode. You can say which is less frequent, so males are less frequent than females. You can say what are the frequencies in this data set, which has 20 females and 10 males. What are the percentages? So if you take those 20 to 10, you get that 67 to 33%. You can take cumulative percentages and ratios, so twice as many females than males that are there. So that's pretty much the ways in which you can describe nominal data. The descriptives for ordinal data, so ordinal level of measurement means data tells you about the order, but not the distance, so the options are ranked. Hopefully that's drilled into you now and you have a good sense of ordinal data. Descriptive approach is the same as for nominal, but you can also use percentiles, including the median. So those are additional descriptives available to you. For interval data, level of measurement conveys information about the order and distance, but the zero is arbitrary or not meaningful. So you can describe this data in a number of ways using central tendency, so the mode, median, mean, the shape, looking at minimum and maximum values, the range, standard deviation, skewness, and kurtosis. Interval data is discrete, but often treated as continuous, especially if there are more than 5 intervals that are there. So this is what I was raising previously in terms of the contentious issue in research that uses Likert scales, is that it treats this data as continuous, and for the purposes of this course, we'll treat it as continuous. But there's good arguments to say, well, is it truly continuous, or is it more ordinal, because it's 5 distinct categories, 1, 2, 3, 4, 5, and what is the meaning of differences between 0 to 1 versus a 4 to a 5? But for the purpose of this course, we'll treat it as continuous, and this argument is stronger, especially when you have more than 5 when you have 7 or 9 intervals. It's more stronger to be able to say it's continuous data than it is ordinal. And descriptives for ratio. With ratio, the number conveys the order and distance with a meaningful 0. Again, hopefully that is reflexive for you to be able to say and think and understand at this stage. So use the same descriptives as for interval data, but you can also use ratios. So you can say group A is twice as tall as group B, right? So this is some of the descriptives you can say with ratio, and you could provide precise numbers in relation to those ratios. And so for the summary of descriptive statistics, the level of measurement and normality of your data determines whether data can be treated as parametric from the sort of flow that we had previously. You can describe central tendency using frequencies, percentages, mode, median, and mean. And you can describe the distribution using minimum, maximum, range, quartile, standard deviation, and variance. So that's really the key summaries of descriptive statistics that we've talked about. So what we'll do now is we'll talk about the 4 moments of a normal distribution. So these moments relate to the mean, the standard deviation, the skewness, and the kurtosis. And so the mean is in a perfectly normally distributed plot. We have the mean as centered. The standard deviation represents the spread that we see. The negative skew is, and positive skew relates to whether the data is shifted on one side or the other. And kurtosis is sort of this explanation of the peaks of your data. And I have some further examples to share about this. But before I go into that, I want to talk to you about a really cool property of a normal distribution, which is this rule called the 68, 95, 99.7% rule. Not a very, it doesn't flow off the tongue, but it's probably one of the most powerful rules and statistics that you can use to understand data. What this rule states is that in a normally distributed data set or variable, what you have is 68% of the data fits within one standard deviation of the mean. So if you take the mean of a data and you take one standard deviation of it, 68% of the data should fit within there. And then if you take 2 standard deviations from the mean, 95% of data should fit within there. And if you take 3 standard deviations of the mean, 99.7% of the data are within 3 standard deviations. So I said earlier that there are papers that are done where you can, sometimes they report the standard deviation in the mean for data that may be skewed, and you get a sense that the data may be skewed. Well, how do you work this out as to whether or not the data is skewed? You can actually use this trick to get a sense of it. So for example, let's take the age of participants and say the age of participants is 60 and the the average age is 60 and the standard deviation is 10. From that, I can already work out that for most of the data set, 68% of the data will fit between 50 and 70. How? Because you have, if 10 is the standard deviation, so you subtract the standard deviation from the mean, which gives you the 50, and then you add the standard deviation to the mean, which gives you 70. So if the mean is 60 and the standard deviation is 10, you get 50 to 70. So that's 68% of the data. Then if you do 2 standard deviations from the mean, you get, if the mean is 60, then 2 standard deviations is 40 to 80. And then 3 standard deviations from the mean gives you 30 to 90. So you can get a sense of the spread of the data and how much data should be within it at each of these points. So 99.7% is within 3 standard deviations. And this is really powerful. So when you're looking at descriptive tables in papers, and they report that the average is X, and if they say the average is 50 and the standard deviation is 3, but you can get a sense that the overall data that it encompasses is quite large. So for example, if the standard deviation is 3 and they report the range as well, and you can see that, well, a lot of the data in the range seems to be quite outside of what 3 standard deviations are of this data set. Out of the 3 standard deviations, 99.7% of the data should really fit in there. So more often than not, when this sort of thing is occurring, or it doesn't seem like this rule is mapping on, it's likely because the data is not normally distributed. And in those cases, they should be reporting something more like the median or the interquartile range to get a sense of what the data is. So really useful tool, really gives you a good sense. You can look at what we describe as table 1 characteristics of papers and get a good sense of what each of those measures, what they look like. And so you can map it back based on the numbers that are in that table. So whatever the standard deviation is and the mean, you can now just map that back to work out what how much of the data fits within 1, 2, or 3 standard deviations. So really, really useful tool. Hopefully it's something that you keep in mind and look at when you're critically analyzing papers and getting a sense of the data. So here's an example of a normal distribution. So this is the UK Biobank dataset, which is a dataset I've worked on and published papers on. It's a dataset where they collected over 500,000 participants to be involved in the study, and they collected all sorts of data, including neuroimaging data, genetics data, health data, and here I've just pulled a variable, and you can access all the variables through this data showcase online. And I've pulled this data, which is height, I believe it was, yeah, height. So I looked in height, and you can see that this is what a normal distribution looks like in real data. So you're not going to get something that looks like this perfectly. In real data, it maps on as close as you could see. But you can see that there's gaps here, and that's probably a reflection of perhaps the sampling or the population. But on average, this would be something that we would term as a normal distribution. It's quite symmetrical and centered around that mean there. So there's not a lot of skewness, or if any skewness, that's occurring here. So I just wanted to show you what that looked like, and you can look into variables in this data set, go into the data and see, well, is this negatively skewed, positively skewed, or normally distributed? And we'll talk about positive and negative skewed right now. So skewness, you can think of it as a measure of the lean of a distribution. And so the way to think about it is that in negative skew, much of the data is shifted on the right, and in positive skew, much of the data is shifted on the left. So how do you remember this? The way I keep it in mind is when I think of a distribution, if I think negative on the left, you have from the x-axis 0 to thing, I think the negative values are on the left side. And so if all the values are pushing to the right, then it's wherever the tail is. So the tail's following the negative side of the plot, so that means it's negative skew. If the tail is following the positive side of the plot, it's positive skew. But whatever really works for you, as long as you take away from the fact that in negative skew, the distribution of data points is more in here, in what you see in the plot, and in positive skew, more of the data is here. Sorry, I was just looking at the camera to make sure it's not flipped in the other way. Trust the visual that you see on the screen here. So you want to look for the tail where there are fewer values. So if the tail's to the right, it's a positive skew. If the tail's to the left, it's a negative skew. What causes skew? Well, outliers. As we saw with that example earlier with the hygiene factors, we could see that when the outlier was present, we had this positive skew that was there. And then without the outlier, we have this normal distribution. So outliers can certainly influence skew or cause skew. There's also floor effects that can emerge. So this includes if a measure is difficult to score highly on. So for example, if you ask people how much vigorous physical activity do they do in a week, most people will be on the lower end of that scale at a population level. And so you'll get a cluster of values around the lower end of a scale. If you give people a very easy cognitive test, you get a lot of high scores, and so that's where you get ceiling effects, where much of the scores are close to 100. So how do we work this out? Well, we check the chart and see what's going on. So once you have a look at the chart and get a sense of where the values are clustered around, you can get a sense of the skewness that's happening. Now, skewed data is not always a mistake. Sometimes it's a nature or a property of what you're studying, the phenomena that you're looking at. So here's an example from my research where I was looking at the time it takes for people to get a dementia diagnosis. And each of these groups represents a different type of dementia. So you may be familiar with Alzheimer's disease. That's here in AD. There's other types of dementia, including frontotemporal dementia, the most common being behavioral variant frontotemporal dementia. There's also semantic dementia, and it goes on. But the main takeaway I want you to know from this plot is to see how much of the data is sort of distributed around the first few years. This is time it takes to obtain a dementia diagnosis. And so most people, it seems, obtain a dementia diagnosis within 0 to 6 years, or 1 to 6 years, it seems. And there are some outliers here where some people it takes quite a long time, but more often than not, all this data is positively skewed. So the tail's on the positive end. And so here's an example in where the reality is if someone notices for Alzheimer's disease, for example, that something is occurring with their memory, or maybe a loved one notices it, then they're more likely to go and see a doctor and go through the pathway of obtaining a diagnosis than not. And so that's where you see in this phenomena that we're investigating, it's quite natural to see this peak and then have the tail that's there. So that's what we'd expect in something like this. So here's an example in real data of skewness and how it's a property of the data that you're looking at. Now, kurtosis is really how flat or how peaked the distribution is. So peak data has positive kurtosis and flat data has negative kurtosis. And really that gives you a sense of the tails and the presence of outliers as a function of that as well in terms of kurtosis. So a distribution can look more peaked or flat depending on how the graph is set up. So you can on the x and y axes, if you spread out those values or condense them, it can impact what the kurtosis visually looks like. So you need to add a normal curve to really judge kurtosis visually. And so here's an example of a plot I made to really sort of emphasize what each of these differences are within kurtosis. So you have platykurtic plots where you have this sort of flat distribution and very thin, if not hardly any tails that you see there. So there's no outliers here. It's all just all the values are within this distribution. You have mesokurtic, which is similar to a normal distribution of what you'd expect to see. And then you have leptokurtic. So leptokurtic is a quite peak distribution. You have fatter tails that are there, and so you have more values that are there in the outlier. So what we see is each of these distributions gives you a sense of the peaks and the tails. So hopefully that's something you can keep in mind, and a useful acronym or way I use of remembering this is platykurtic, sounds like flat, so that's what it looks like, platy, flat. Lepto, I don't know. Maybe I'll leave that to you to work that one out. So how do you judge how severe the skewness and kurtosis is? Well, you check the histogram like we just did there, right? So the histogram gives you a sense of the skewness, and that's what we see there, and as well as the kurtosis. Ask yourself, are there outliers? If so, deal with them. And what I mean by that is, should the outliers be there? An example such as this, the outliers made sense and they were plausible, so we retain them. But in cases where the outliers may not make sense, maybe you have an argument for removing those values. You run the skewness and kurtosis analysis, which will give you a significance, a value and a significance for the test. Now, rule of thumb is that skewness and kurtosis values between -1 and +1 is generally normal enough to meet the assumptions for parametric inferential statistics, but many use plus or minus 2.5 as the cutoff. Now, in statistics, we use these cutoffs and we have these standardized rules to help students as a framework, but really each of these are guidelines and there's nuance to each of these guidelines. So for example, for these statistics, when you have really large data sets, they're really sensitive to skewness and kurtosis. And so you may have like a tiny bit of kurtosis that's occurring or skewness that's occurring, and it'll be significant in a large data set. And so in those data sets, typically we don't use these statistics. We visually look at the histograms and get a sense of the shape of the distribution. So this is an emphasis of justification always matters. And you look at your histogram, you say, this is what it looks like, this is what I think, and then you publish that. And that gives you a good sense of that. So significance test for skewness tends to be overly sensitive, particularly in large data. So it's not often used in really large data sets. What are things to look at on non-normal distributions? Well, how many peaks are there? Is it one peak, so it's unimodal, like a normal distribution? Is it two peaks, so it's bimodal, right? Or is it more than two peaks, so it's multimodal? And then is there a tail? Is the tail to the right where it's positively skewed, or is the tail to the left where it's negatively skewed? And then how peaked or flat is it? Which is the kurtosis? If it's flat, it's platykurtic, and if it's peaked, it's leptokurtic. And that gives you a sense of also the tails that are there within those distributions. Excellent. Okay, so I'm going to pause there. I'm going to fix this slide, and then we'll come back and you'll have a nice visual of this slide in a moment. So I'll see you very shortly.